Our last speaker of the afternoon is Andrea Dotto speaking on modular representation theory of p-adic groups.
Okay. Hello, everyone, and thank you very much for the opportunity to speak here. So this talk is going to be about a modular representation theory of reductive p-adic groups. One would like to understand such representations as part of a Langlands type correspondence. So one would like to have some relation with Galois theory. And as you try to do that, there are many new phenomena that appear with respect to the situation in characteristic theory. And today, given the time constraint, I would just like to focus on a specific example. So I'm going to work with the p-adic group GL2QP. So those of you in the audience who are familiar with this kind of ideas will know that this is the only group for which we have a satisfactory p-adic Langlands correspondence. And for technical reason, I am going to restrict to the case in which the prime number p is greater or equal than 5. And I am going to work with a finite field of coefficients. So I'm going to fix a finite extension k over fp. Of course, this p is supposed to be the same one as that. So modular is always going to be in p modular in this talk. And it is going to be a finite extension. And this talk is going to be mostly about two objects, which I want to introduce now. The first one I'm going to call Hurley A.
Can I ask you to write larger?
Of course. Yeah. So it is going to be the category of. Is this good?
Yes. Better.
Okay. It is going to be a category of representations of G. I'm going to work with the so-called smooth representations. This is a natural condition to put representations of p-adic groups. And if you're familiar with the situation in characteristic theory, then that's exactly the same condition. And I'm going to need to fix the central character of my representations. I'm going to work with a fixed central character, which I'm going to call zeta. And the second object that I want is a geometric object that I'm going to call X. This is going to be a very simple projective variety over my field of coefficients. So there is going to be a chain of projective lines with ordinary double points. So these are projective lines over K. And this is the kind of thing that you can actually draw. So let me draw a picture of that for you. So it's supposed to look this way. And of course, once you have such a configuration, the only thing that you need to know in order to have complete information about this is how many lines there are. So I want for there to be p plus or minus 1 divided by 2 lines. And the sign in here is a subtlety that depends on the parity of this central character. I'm just going to say depending on parity of zeta. And today's talk is about relating these two objects and also introducing a third player in this game. And the third player is going to be a modular space of Galois representations. So today I want to relate this category A, this projective variety X, and the modular space of two-dimensional modular representations of the absolute Galois group of QP. So in the modular space of, I am just going to write PLQP going on to GL2K representations. I'll be more precise about exactly which modular space I'm in a moment. So in order to make such a connection, I am going to go back to fundamental work of Colmez. So Colmez constructed a mod P Langlands correspondence for this group, and this takes the form of a functor. So this functor goes, is usually called V. It goes from a subcategory of my category A, which I'm going to call A thin. This is just the subcategory, the full subcategory on objects of finite length in here. It goes into the category of K representations of Gal QP. And this has many good properties, which I am not going to be able to list in entirety right now, but I just want to recall one of them, possibly the most important one, which is the local global compatibility property with the completed homology of modular curves. And the reason I am recalling this is that it is the one with the most famous applications of this theory, so including local global compatibility. With completed homology of modular curves. And it is this property that makes the p-adic Langlands correspondence central to all currently known proofs of the Fontaine-Mazur conjecture for GL2 over Q. And for this reason, it would be, of course, very interesting to have such an object for other kinds of p-adic groups. But it turns out that even for groups that look very similar to GL2QP, the situation is a lot harder. So for example, already for GL2 over a finite and ramified extension of QP, so already for GL2 over QPF, a ramified extension of QP of degree F, the representation theory is a lot harder. And for instance, the irreducible representations appear very hard to classify and do not exhibit an obvious link with Galois theory. So representation theory is a lot harder. And the irreducible representations are hard to classify. The hardest one are the so-called supersingular ones that are the multi analogs of supercuspidal representations. So what one tries to do is to look for properties of the Fenter that we already know that have some hope of generalizing to other groups. And the property that I want to focus on today has been proved by Pascunas. And it has to do with the structure of this category A of representations. So Pascunas proved that V induces a bijection. I'm going to tell you the target of this bijection first. So this Fenter V induces a bijection. Which lands into a specific kind of Galois representations. So it lands into two-dimensional semi-simple representations. With the same coefficients as before. And in order to be completely correct, I should tell you that I am going to fix the determinant of these representations. The determinant is supposed to be via local class field theory the same as the central character as before, but twisted by the cyclotomic character. And it turns out that this semi-simple representation parameterize the blocks of this obedient category A. So in this talk by block, I simply mean an equivalence class of irreducible representations where we consider two irreducible representations to be equivalent to one another if they can be connected via a chain of extensions. So there is not a semi-simple category, there are extensions in there. And via the extensions, we can partition irreducible representations into blocks. And in general, following general principles in representation theory, one would like to understand these blocks by relating them to an object that has already appeared in some form in one of today's talk. So one would like to relate the blocks of A to an invariant of A, to another invariant of A, namely the spectrum of the bursting center. Really, here I'm in the maximal ideal spectrum. So to the spectrum of a certain commutative ring, which is called the Bernstein center of A. And if you've never, so there is a commutative ring that acts on every object of the category A in such a way that all morphisms in this category are automatically equivariant for this action. And that is just defined to be the endomorphism ring of the identity functor. Okay. So it acts on all objects by definition. So one knows that if two representations are in the same block, then the center is going to act on them by the same infinitesimal character. And in general, one would like to relate the blocks to the maximal ideals here. But in this case, there is a complication because we can actually prove something about what the center is. And this is very much different from the situation in characteristics theory. So it turns out that the spectrum of this ring is very small because this is just a local ring. The local ring, so of course it doesn't have many maximal ideals. It has only one. And it turns out, however, that even though this looks like bad news, there is a hidden geometric explanation to this behavior. So it turns out that this can be explained geometrically. And so let me state a theorem to this effect. And it is in this theorem that we will see the appearance of the object that I called X. So this is joint work with Matthew Emerton and Toby G. And says that first of all, these blocks of a category A, apart from being in bijection with certain semi-simple Galois representations, they are also in bijection with the close point of that chain of projective lines. And this bijection, I mean, we actually construct a specific bijection with interesting properties. And let me just write this down. So the blocks of A are in bijection with close points of X. And
when you say the blocks of A, you mean
yes,
the set of blocks, or do you mean the irreps within a given block?
I mean the set of blocks. Yeah. These blocks are they're either singletons, so they contain at most 4 representations. Most of them contain 2 of them, and there are some singletons. So yeah, I really mean the set of blocks. With the close points of X. And really, this bijection has to be understood as part of a localization result. So I'm going to state it and then to explain it in a bit more detail. It turns out that A extends to a stack of abelian categories on the Zariski sides of this scheme. So A extends to a stack in abelian categories. On the Zariski side of X. So more precisely, whenever I have a Zariski open subset of X, I can attach to that a localization of A, meaning a Serre localization. So to each U contained in X, and there corresponds a localization functor. Which I'm going to call J of U. This goes from A into, so as I've said, this A of U is really an abelian category that is obtained from A by localization at a Serre subcategory. And these functors fit together into a fiber category over X. And this fiber category satisfies the axioms for Zariski descent. So the resulting fiber category so I'm just going to call a bullet going down to X is a stack. So this can be understood as a localization result, meaning that whenever I have an object of A, and I just draw attention that I could mean a non-admissible object here, this representation can be interpreted as a sheaf over this scheme. And if you do that, then the operation of taking the stalks of this sheaf corresponds to pass into the blocks of the category. And I had promised that I would have related all this to a third object, which is a modular space of Galois representations. So I will finish this talk by doing that. And just an immediate application of this theorem is that I can build a new sheaf of rings on this topological space. So I can attach to every Zariski open subset the center of a localized category A of U. And this just by a formal argument turns out to be a sheaf of rings, but we can actually prove by the same argument that tells you that this is a stack, we can prove that this is a sheaf. So this gives a sheaf of rings. So I'm going to call O of X on X. And some work in progress tries to tell you what the resulting ring space is. So it should be possible to relate this ring space X of OX to a modular space of Galois representation, namely one of the Emerton G stacks. So the Emerton G stack for two-dimensional representations of the absolute Galois group of QP. And this is what's the object that is usually called curly X to QP. So there's the modular space of two-dimensional representations of K, Gal QP. And just to give an idea of what this relation should be, we expect that XOX should essentially be the coarse modular space of this stack, where one needs to make precise what coarse modular space means, but I don't want to do this in this short talk. So this object here is not an Artin stack. This is a formal algebraic stack. So the notion of coarse modular space, needs to be made precise, but there should at least exist a map. There should be a formal scheme, and there should exist a map from X to QP to here, satisfying some good properties of X2 of QP. Okay, and there is an obvious question that is left open by all this, which is that by this theorem, the blocks of a category A have a non-obvious geometric structure in there. They can be identified with close points of a scheme over which the whole category localizes. And so the question is whether such a similar geometric structure can exist on other categories of p-adic groups, on categories of representations of other p-adic groups. So this is something that is very much open, since the representation theory of other groups looks a lot harder than for GL2QP. Is there a similar geometric structure on categories or modular representations of other groups? And if such a thing existed, then it would be interested to try and relate it to coarse modular spaces for other modular spaces of Galois representations. Okay. And with that, I think I'm going to stop here. Thank you very much for listening.
Any questions for the speaker?
Could you tell again what a fin was meaning?
Yes. So if in A, it's just supposed to be of a full subcategory. On objects of finite length.
Ah,
So how does OX relate to the structure sheaf of the chain of P1s that you mentioned?
Yeah, so far that's part of a work in progress. There should be the chain of P1 should be the underlying reduced. So this should be a formal scheme with underlying reduced given by the chain of P1s.
Do you know that XOX is a formal scheme?
No, that's what I'm saying. So we have some computations of what this one here is, and we essentially have a computation away from the away from these crossing points. So if you localize away from this, then yes, then the answer would be yes, but not for the whole thing yet.
Is there a derived structure, a higher structure that you can compare on both sides?
So not that I know of. I will say that this object here so has a natural, so I am not too good myself with derived structure. I know that there is a natural complex in here that should give you some kind of abstraction theory, and that's the Hare complex. So there should be some, there are hints of such a thing, but I don't know too much about that side of things.
Any other questions for the speaker? All right, let's thank the speaker again.
Thank you.